shear flow problems, fastener spacing problems, have the #1 most common student mistake in the entire semester of mechanics of materials, and this is Q, the first moment of area, which everybody just knows as Q. So in this problem, I'm trying to find the maximum shear in the beam, and as a result, then the maximum nail spacing. What's the largest distance apart I can put nails so that the beam is not gonna fail, or so that the nails won't fail. So my main equation is gonna be Q, which is shear flow, that's lowercase q, equals V capital Q over I. Capital Q being that first moment of area, that thing that everybody hates, V the shear force, and I the area moment of inertia. Now fastener spacing is going to be S is the spacing in like inches, equals F over Q. F being the maximum force that each nail can support, and then lowercase q being that shear flow. So I can combine these two equations since they both have lowercase q in them, they both have shear flow, and I can get that S, fastener spacing, is Fi over Vq. So I just need to find those four things, good to go. Sounds like an easy problem, but this is, again, one of the hardest problems with the most students' mistake you'll see in the entire semester. All right, so first, if we're trying to find V, the maximum shear force that would not result in the wood breaking. So shear force, this is transverse shear equation. Tau is VQ over IT. So we can rearrange this. Tau IT over Q is the shear force. So we're given tau. This is the strength of the wood, 400 psi. T is going to be the thickness. And so we're going to grab the thickness at that 1 inch right in the middle of the wood. When a beam fails due to bending, the maximum bending stress is always going to be at the very top or the very bottom of your beam. Shear is exactly the opposite of that. The maximum shear is going to occur right in the very middle. And the reason for this is because that's where you are separating the most amount of area. When you have your value for Q, capital Q, that first moment of area, that's going to be largest when you're looking at a place right in the middle because you have a ton of area up above it. At the very top of your beam, where bending is the largest, you have no area up above, and that means your Q is going to be 0. The place where you have maximum bending, you have 0 transverse shear. All right, so the dreaded Q. Q is a sum of y bar prime, a prime. So y bar prime meaning like a centroid, so a centroid of a piece, and a prime meaning an area. So you're finding a location times an area and adding those together. So this is going to have units of like meters cubed or inches cubed, right? Distance times area is going to be a distance cubed. So from our centroid of this beam, we can look and see that we've got essentially 2 rectangles up above it. Just the little skinny vertical rectangle and then the big wide rectangle for the top of the eye. So I'm going to have 2, y bar 1, area 1, plus y bar 2, area 2. But before I can actually finish this, I'm now going to have to find where that centroid is. I just drew this arbitrary line here, but I don't actually know y bar, where the actual centroid is located. So now we dive deeper into the rabbit hole looking for centroid. To find the centroid, we look at the entire I-beam, which I'm going to split up into 3 different rectangles, a horizontal one at the bottom, vertical in the middle, horizontal at the top. I'm going to measure my centroid from the bottom, so I'm calculating my 3 areas, 15, 12, and 9. And then I need 3 distances. All 3 distances are going to be measured from the very bottom. So I've just got 0.75 up to the bottom one, because it's 1.5, so half of 1.5. Then I've got 7.5 to the middle, the 1.5 at the bottom, plus half of 12 is 6, so 6 plus 1.5, 7.5. And then the top one, 14.25. We've got the 1.5 plus 12 plus an additional 0.75 for half of the top. So calculating a centroid is just a weighted average. It's pretty much the same way you calculate a GPA. So I've got all of my distances and areas in the numerator, and then the denominator is just the areas. And the result, when you have distance times area divided by area, you're left with a distance as your weighted average distance. So 8.625 is my Y bar. That is the height from the very bottom up to the centroid. All right, so areas first. The top rectangle is going to be easy. It's just the same 15 that we already found before. For area 2, this is the area of the small sort of sliver of vertical here. So the top of that rectangle is at 13.5, right? The 12 plus 1.5. So the top is at 13.5 minus the 8.625 gives a height of that rectangle of 4.875. So for the Y bar primes, if 4.875 is the height of that rectangle, half of that height, the 2.4, is going to be the Y bar prime. So the distance from the center of that little rectangle back down to the centroid. Y bar prime 1 is going to be from 14.25, the height of the center of the top rectangle, minus the height of the centroid, 8.625, we get 5.6. This is the Y bar prime 1. So we solve for Q by multiplying area times distance, adding them together, 96.26, and I did not add units here, but that should be inches cubed. It seems like we've already solved a million problems in this problem, but we still can't even find V yet. We still need moment of inertia. These problems are very long. So moment of inertia for a rectangle, 1/12 BH cubed plus AD squared. For that, AD squared is the parallel axis theorem. So we're going back to look at the centroid again, where I have all my sort of areas and lengths written out. So we have, again, I'm going to use those same 3 rectangles, the 1/12 BH cubed, for each of these 3 rectangles. So the base is always the horizontal. So it's going to be like 6 and then 1 for the middle and then 10 for the one on top. And then height is always the vertical height. So only 1.5 for the bottom one, 12 for a height in the middle, and only 1.5 height for the top one. My AD squared, this D for the parallel axis theorem, is sort of like Y bar prime from solving Q. It's based on the distance from the center of these rectangles to the centroid. So finding moment of inertia is very similar to finding Q, except moment of inertia involves both the top and the bottom half, right? The entire cross-sectional area. But Q only looked at half of the area, only the area above the centroid, which we could have also done the area below the centroid, right? Above or below, take your pick. So here in my D squared in this equation, the 14.25 is that Y bar 1, Y bar 2, 7.5, and then this Y bar for the bottom one, 0.75. All right, so do all the math, plug it into the calculator. 1196 inches to the 4th. So another difference, area moment of inertia is inches to the 4th power. Q was only to the 3rd power. It was a distance times an area. The area moment of inertia is BH cubed, right? You've got 4 length terms in there, so inches to the 4th. And now we can finally go back to V and actually solve for the first part of the problem. We're not even getting to a final answer. We're getting to one of the final answers. So V is the 400 pounds, the 1196 inches to the fourth, our thickness, which is just that thickness right in the middle, divided by Q, and we get to a maximum shear force of 4,970 pounds. Or you could do 4.97 kip if you wanted to work in kilopounds. So moving on, fastener spacing, last step, maybe, probably not. S is equal to Fi over VQ. Now, finding Q was such a pain to do the first time. Unfortunately, this is not the same Q that we solved before. Capital Q, when we solved before, we were worried about the wood breaking. So we solved for Q right at the centroid, the place where shear was going to be a maximum. But if we're worried about the nails failing, then we only need Q at the place where the nail would break. So for this built-up beam, if the nail at the top were to fail, the wood down by the centroid is not what would break. The part of the area that would fall off if the nail broke is only the top part of the beam itself. So we need a new value for Q, and in fact, we'll get two new values for Q. One for the nails at the top of the board, and one for the nails down at the bottom, assuming what if the nail failed and the top board fell off? What if the nail at the bottom failed and the bottom board fell off? So it's still Y bar prime A prime, but now instead of having to account for the vertical sliver in the middle between the centroid and the top board, we're only looking at the top board itself. So only that area 15 and that Y bar prime 14.25 minus 8.625, or in the bottom half from 8.625 down to 0.75. So we get a Q value for the top row of nails of about 84. This is going to be inches cubed. And Q for the bottom set of nails based on the bottom board's area and distance of about 71 inches cubed. And you might already be predicting, since these values for Q are different on the top and bottom, you'll actually get different minimum nail spacing for the top and bottom. They won't end up being the same. Now, the 400 pounds is the same if the nails are the same. The 1196 is the same because it's still just one I-beam, the full area. 4970 is still the same. That's still the maximum shear force. But a different value of Q for the top versus bottom nails is going to mean on the top, 1.14 inches is going to be your maximum spacing. And on the bottom, 1.36 inches maximum spacing. All right, I'm sorry this video took a million years to finish, but if you learned something, if this helped you out a little bit and you want to do a favor for me, go ahead and hit the subscribe button. I know it's a stupid vanity metric. I know the numbers don't count, but I'm vain sometimes. I like seeing that subscriber count go up a little bit, so I'll consider it a huge favor. And have a great weekend, have a great rest of your week, and good luck on your next test.